It's my pleasure to give this talk of the joint work of my excellent co-authors and myself. And this was actually a collaboration between 3 institutes. So firstly, the Ruhr University Bochum, where I'm also originated. And secondly, the Technology Innovation Institute in Abu Dhabi and the Paderborn University. So to set a common ground, let's first recap a few attacks, side channel attacks. So we already heard today about the Bleichenbacher attack. There's a Lucky 13 attack, or a padding oracle attack. So these are all known attacks, and in statistical timing side channel attacks, these are well known. And since we want to talk about statistical timing side channel attacks, let's first set a ground. In cryptographic timing measurements, a protocol should always have a secret independent execution time. And if that is the case, let's take 2 inputs. Input vectors x and y, and think of them being, for example, a valid padding versus an invalid padding. Then we have 2 theoretical distributions, and if these are now different, we can expect to have something like a timing side channel. And obviously, as I said, usually these distributions are not known, so we have to collect measurements. And if we collect these measurements, here's a really high overview how this could be done. Essentially, we have a client and a server. We have our input vectors x and y, and what we do, we let the protocol run and then measure the time. And now we have a collection of data, x1 to xn and y1 to yn, of our input vectors x and y. And now if the execution time is secret dependent, these 2 histograms should look different. So we should be able to tell them apart. So what statisticians then usually do is they compute some type of summary statistic. And most of you probably know the t-test. But what there's done basically is computing the mean, and then if the means are close to each other, then we expect these distributions to be the same. If the means are not close to each other, they're different. And in this picture, you might not even need statistics. You might just say, okay, I can see these distributions are not the same. And to get to the tool we are proposing, we deviated from the classical just differentiating distributions by the mean. We have considered quantiles. And for those who are not aware what quantiles are, the 50% quantile is essentially the median. And this is probably what you already know. And what we have done, we have considered different quantiles, computed their differences, and if these differences are close to 0, then we expect these distributions to be the same. If they're not close to 0, they are different. And obviously, as I said, we are collecting measurements. And when you're deciding on something based on measurement, there's a possibility of making a mistake. And to put this into a side channel perspective, think of the following. If in reality, there's a side channel, and our test actually says, no, there is no side channel, we cannot tell these distributions apart, then this is what we call a false negative. On the other hand, if there is in reality no side channel and our test says, hey, there's a side channel, this is what we would call a false positive. And a common approach in statistics is to handle this and balance these 2 errors is the following. What we do, we prescribe a false positive rate, which we usually call alpha. And given that alpha, we want to minimize the false negative rate, which we usually call beta. And obviously, you can see these are 2 conflicting errors. So there's a balancing part involved. Okay, and now I come to the tool that we propose. We call this Airtime Leak Finder, short RTLF. And what we provide is a tool with an adequate trade-off between false positive and false negatives. And some of the previous tools that are often used do not really offer this. And we will see this later on the real-world data set. And as I said, alpha is now an input parameter, and it upper bounds our false positives. And another important property of our test is that the more measurements we collect, the lower our false negative rate will be. And for those who have done statistics prior to this, the method that we have actually used to have an adequate trade-off is once an empirical bootstrap, which is basically a resampling methodology that allows for this trade-off. And secondly, we have used the Bonferroni correction, which basically addresses the multiple testing approach. But to not bore you with statistics, let's get to the real-world application. So we have considered TLS implementations, and in this case, the most prominent one OpenSSL. We have set our false positive rate to be below 0.9%. And the image you can see now, the x-axis is essentially a version line. So these are all the versions that we have considered. And on the y-axis, we have these different attack vectors. And these attack vectors are all from the literature, so well known. And on the top, we have 10 different pairs of Bleichenbacher vectors. In the middle part, we have padding oracle. And lastly, lucky 13. And now you might be a bit overwhelmed. What is this picture? Let me just get to the color encoding, and then I think you will be fine. So essentially, the green color indicates that our test didn't detect a timing leakage. So the distributions were the same for us. In the rest of the picture, the color, any color indicates a timing leakage, starting with yellow, where there was a minor timing leakage, and the darker the color gets, the larger the timing leakage. So basically, in simple words, the darker, the worse. And a few observations here to make are the following. So first of all, we have some kind of block structure, and this is what we have expected when we started the simulations. Because what we have is usually a vulnerable implementation, and at some point we have a CV where it's fixed, and then we expect it to not be vulnerable anymore. And you see some of these jumps from vulnerable to non-vulnerable, for example, where it's quite clear in the top 4 Bleichenbacher vectors. And a good question now is to ask here is it possible to validate these jumps from being vulnerable to not vulnerable, or from being vulnerable with a large timing leakage to being vulnerable with a smaller timing leakage? And yes, we were able to do this. Let me just plug them in here. I will not go through them in detail. You might be wondering, why is this 2 appearing multiple times? The main reason for this is that these versions were sometimes developed simultaneously. And as you can see, we were able to pinpoint most of the jumps quite accurately. Okay, so with this, as I said, alpha is an input parameter. And to give you a bit of an idea how alpha really impacts it now, as I said, it upper bounds the false positive rate. And you might see that on the top right, we have this one red rectangle, which we thought might be a false positive. So what we said, okay, let's try to lower the alpha. And this is what we did, and what you see is that our potential false positive disappears. Obviously, as it can be decreased, we can also increase it. And what really happens here is now the following. So on the top right, where we do not expect any true positives, we observe now some positives, which we think are false positives, actually. However, on the other hand, if you look at the padding oracle fraction at the beginning, you see a more consistent true positive behavior. And we can stress this one out a bit by increasing alpha up to 18%, where we have more false positive in the top right part, more consistent pattern in the padding oracle part at the beginning. All right, now you might ask, Martin, why should we use this? Is there a specific reason? Why can we not use the previous tools? And here we have chosen what we think is the most prominent tool used in TLS, DUDEC. What DUDEC basically does is it computes multiple t-tests on subsets of the data they collected. And if the sample size here is now 30,000, you see essentially that DUDEC does not really detect anything except the really major side channels at the beginning. In comparison, at TLF, with a reasonable false positive rate at most 0.9% and sample size 30,000, it is exactly the same data set. We detect them quite consistently. If we then again increase the sample size, as I said, the false negative rate will decrease then. TLF detects, I think, the pattern quite reasonably well again, while DUDEC only detects the major side channels in the Bleichenbacher. Okay, so with this, let me sum it up. So basically what we think, we have provided a statistical tool with a usable trade-off between false positive and false negatives. We empirically outperformed basically all of the existing tools. And for those who are interested in, we have conducted a large-scale real-world evaluation on 11 TLS libraries in 823 versions. And in more recent versions, up to 2022, we have found 7 vulnerabilities. And for those who are interested in the comparison to the other tools, we have many more visualizations of this form in our paper. And if you're interested in using RTLF, feel free to check us out on GitHub. And yeah, please ask any questions, and we are happy to exchange. Thank you.